Okay, hi everyone, welcome back. In today's video, we're going to be having a look at strips modeling. So this is kind of a continuation of our classical planning adventures. So we're going to start modeling real-world problems, right, in some form of formalized language, some form of formalized framework that enables us, right, to describe the complicated real world, right, with its infinite complexity into something with very, very simple formal definitions, something that we can essentially efficiently computationally solve, reason over, compare, and in a way that's generalizable, right? So you'd be able to extend this model if you want to change things about the way you want to model the problem, or if things change in your worldview and you have new information you want to weave in or take away and so forth. So STRIPS stands for the Stanford, so the T is a bit of a cheat, the Stanford Research Institute Programming? No, it's Problem Solver. The Stanford Research Institute Problem Solver. I get that wrong every time, and hence why I have an entire screen up just for the acronym. This came out of the Stanford Research Lab. It was used with the Shaky robot, which was one of the first ever AI uses to have a robot move around and complete some simple tasks in a room, like flicking off switches, moving blocks, things like this. So STRIPS was very, very exciting. In next video, we're going to have a look at something called PDDL, so Planning Domain Definition Language. That is essentially the modern equivalent to STRIPS, and it's kind of the one that is moving forward in the research and enables us to be much more verbose and expressive in the ways we want to represent these problems. But STRIPS is the foundational concept, and the beauty is, like, through learning STRIPS, you learn PDDL, right? They're essentially going to be the same. PDDL just builds slightly upon these ideas. So this is extremely fundamental, and you do need to understand STRIPS, okay? So let's kind of get to try to describe it and talk through how we're going to model the world. So the first thing we're going to do is essentially, right down here, I've kind of written it up to guide us through this. Whenever we're trying to define a problem through STRIPS, well, we essentially have, sometimes it's called FOIG, sometimes it's called FOIG, whatever you want it to be. We're going to define this in terms of almost like two pairs of things. So the first one is going to be that F or S, you're either defining like how all your possible states can come about, or I like to think about it as you just need to define all the facts, and predicates is a fancy word, but we'll get to that. You just need to define all the things you need to know about a world in order to describe it, okay? So that will be things such as objects, constants, facts, as well as when we get to predicates, this is kind of checking information about objects. So hey, this block B is on top of another block, okay? So that maybe is something we want to reason about and to check and be able to express about the world. We'll get to all of that when we start doing this. Then O is the set of operators, okay? So we describe things and we interact in the world, of course, through a series of operations, through a series of actions, right? So any agent, right, human being, robot, that is how we solve problems, that is how we engage with the world. We look at the facts, right, we recognize the environment around us, and then we take a sequence of actions to attempt to go from some form of I, initial state, initial situation, such as this, to whatever our goal state is, right, to achieve something, and we have an achievement in mind, okay? So in this problem over here, we'll get to it, but in the block spot example, it's a really, really beautiful problem description that I think is really great for learning how to use STRIPS for the first time. Here, the goal is to actually stack all the blocks so that they're in alphabetical order. So it'll be like A, B, C, D, E, okay? And so E would be the one at the bottom on the table. So let's get into talking about STRIPS. So we have a bunch of fancy words that we're going to try to define. We're going to define what they are in terms of this problem. We're going to come back and then actually write up and then actually kind of essentially be able to draw transitions in the search space to be able to solve this problem, to generate how we would possibly get from this initial state to an actual solution. And it's way easier than you think. So let's first talk about the idea of constants, okay? So constants are, I would kind of describe, I guess I'll write them in blue as another English word that I like associating with them. I kind of think of these as objects, okay? So constants are named things in the world. You would be able to name them anything you want. But in this kind of situation, right, why don't we just go with the fact that we have all of these blocks, right? We have A, B, C, D, and E. In the blocks world example, we have what you call as a little crane, or whatever you want to call it. And this is going to pick up blocks and move them around. So there's a world situation where you could also, if you wanted to view the world that way, write that the crane is actually a constant itself. I won't do that, and I'll show you how oftentimes we make decisions to simplify the example, which works just as well and is, I think, just as intuitive. We're going to deal with that in terms of the actions you can do instead of a constant. Okay, so next is variables. So I'm not going to write a second word for this. The variables is, I think, very easy to understand. This is just like when we go to program in any random language. It just means usually we describe the actions and the things we operate on, similar to functions, over a generic term, right? So when we write code, when we write strips, we don't actually put in A, B, C, D, E, whatever, right? Which block do we want to pick up, for example? We write it first, we write up the action, the operator of pickup in terms of generic variables, right, instead. And then when you go to solve the problem, that's when you decide, oh, which one of these blocks do I want to pick up? Should it be B? Should it be C? So forth. So variables are just a useful programmatic aspect of this language. Then we get to predicates. So these are also called fluents. I kind of like to call them facts as well, things that we can check and reason about over the world. So let's reason over what some predicates are that we actually need to know. So we know that as human beings, we look at this kind of problem and we see additional information, right? There's obviously something clearly different about the idea of blocks being stacked, right, or on top of each other than just on the table. So here are a few ones that could be useful, right? We might want to check if something is on a table. And again, you could write this any way you want. This is the beauty. You're translating a real world problem into some human understandable language, and we're still able to model the world this way. So you want to check that something is on a table, right? Okay, C, A, and D are on a table. That's something we want to check about the world. This is where like the idea of the variable comes in, right? That's helpful to check that, hey, what is on the table? We're going to pass in a variable, which will in the future be an actual object. Something else, as I just said, is like this idea of something being on something else, right? So on top of, on, whatever you want to call it. And this is different because you're checking two things, right? You want to check not just that E is on something. You want to check what block it's on. So this would be similar to a regular function in, say, Python or whatever, right? You pass it two arguments. Hey, is X on Y? I think that makes sense. Now, we want to reason about other things in the world. So we want to go pick up blocks. Well, our crane can only hold one block at a time. Okay? So, for example, you might want to check something like, is the crane holding a specific block? Right? So then we can check what it is holding. But you also might just want to have a default information as well, like just generally, you could just say holding at all, but just to rename it to something different, hand empty. Right? And this one doesn't take a function. This is just another fact we can reason about the world. I'll do this, I guess. Is the hand empty? Or is it full? Okay? So it's just true or false. All of this, I forgot to say, when we're dealing with strips, all of this and everything we reason over is just going to be extremely simple. It's just Booleans, true or false. We are representing the entire world through Boolean information. Anything that is labeled true in a state is true. Anything that is not described is automatically false. At the end of this video, we'll talk about how that is actually a large detriment to strips. And it means that it's hard for us to be expressive in the rules we as humans want to express about the world, and like and/or and things like this, which is where PDDL kind of comes in to be the modern equivalent and to make some of this easier. But again, as we learn this, you're also learning PDDL. The other thing we might want to know, right, is when we want to put a block on top of something, I want to put block C on top of A. Can we do that? Well, no, right? You know that there's you can check on, But you might want to check something even simpler. Is a block clear? A block clear would mean nothing is above it. So B is clear, C is clear, E is clear. Okay, this is not like an exhaustive list. I am making decisions about how I want to model the world here. And you might make different decisions. You might have a greater granularity or less granularity. And there are all these trade-offs either way that are true about this. One thing in that regard, though, is that we often want to strike a bit of a middle ground, okay? So we could describe absolutely everything in terms of these massive, highly specific predicates. Oftentimes this, right, where I just have a handful of things that are useful, that make sense in an intuitive sense, this is going to be enough. But you still want to have this granularity of checking, like, is A on B and things like this, instead of just a single, oh, and the idea of like picking up and putting down, as we'll get to in the operators in a second. Having this additional expressiveness in the sequence of actions means that it's going to be easier for our robot to actually go and do them, right? So if I just said move E to B, right, that could be a more simple problem to describe. But then you go and you pass that to your robot, and it's a little bit harder for the robot to understand how to move a block from any position to any other position, including like where it is in the stacks, as opposed to a robot that says, oh, this one's on top, it's clear, I first need to move the crane, pick up, move the crane, put down, right? So that's always something we have to keep in the back of our minds when we model problems. But anyway, I think here is a very simple example where we're just trying to do something that makes sense. So there are situations, right? The blocks world's an excellent one, because there can be worldviews where there's 4 actions you want to write, or there's worldviews where there's just 2. So I'm going to do 4. Try to keep in mind how you might be able to do 2 instead. So I've kind of said some of this, right? But operators are the actions that we can do. Actions. Okay. Now, well, what are some actions we want? One of them is that we do want to pick up. I'm not going to write out the full actions and like their operators, because I want to write that up correctly over here. And actions are the harder ones to implement. It's where all the code actually kind of comes into play in describing these things, because there's going to be preconditions and effects, and writing that out takes a little bit. So we might want to check how to pick things up, right? We might want to do put down. We might want to be stacking and unstacking. Okay, so this, again, is up to you. I've decided to specify specifically there's 2 different kinds of actions. Instead of having like a generic sense, I'm saying one of them is easy. Unstack is going to be like take B, put it on the table. Stack is going to be take something from the table and put it on top of a stack. Pick up is going to be pick it up and hold the object. Put down is going to be put it on the table. Okay, so let's come across here then and start to draw up some of these actions and what we need. Maybe I'll do it here, and I'll do it in green, pretending like that's distinguishable from the yellow I already have. I'll do a blue line in between just to try to separate this. So let's have a look first, I think, at the, let's do the pickup, I guess. Okay, so we have the pickup action. What are we going to operate on? You want to be picking up, obviously, blocks. So we're going to, again, describe this as a variable. Now, here is where things become important. So for every action, what do we need? We need preconditions. This is the first thing you need to define. When you go to apply actions to the world, human beings intuitively know sometimes things make sense to do, sometimes you can't do something. The computer needs a little bit of help. So in order to pick something up, right, can you pick up a block A? No, we know, right, that there's b's on top of it. So we need to kind of give this information. We need to have a series of facts that we need to check in order to be able to actually make an action, an operator, viable to actually take. So let's reason over this then. What is something we can actually check? Well, one thing that is obviously very important, as I just said, you can't pick up A because it is not, there's something on top of it. It is not clear, okay? So one thing that we might want to check is that X is clear. There is nothing on top of X. That's nice. Depending on the worldview, I described this as a bunch of very similar operators because what I actually wanted was to have different behaviors in terms of whether something's on the table or it's on top of another block. So in this worldview, I'm going to say, just the way I'm writing this up, well, I actually also need that the X is on the table. Okay, so in this situation, you're only allowed to actually pick up a block when it is on the table, so you could only pick up C right now. Otherwise, you would have to do the unstack action, okay? And unstack is where you move it to the table. We're only doing this really because it makes it slightly easier to show you how modeling works and how different actions can have different preconditions, and you could change the way you describe the series of things you need to do and what is allowed. So the other thing, of course, is that because we're actually trying to pick up the block, okay, so we can't pick up A. We actually can't pick up B either because it has to be on the table. If I were to pick up C, there's another fact we need to know about the world before that's something legal that's able to be done. And if you have a think about that, we need to check that the actual crane hand is empty, right? It needs to be able to pick something else up still, so it's not holding something. So we need to check holding is a true fact, right? The really important thing here is I cannot write this. In strips, this is extremely important. Strips is unable to deal with negative, this is a not sign, negative preconditions. So no negative preconditions or effects, as we'll see as well. Okay, so strips is extremely simple. You can only describe the world in terms of Boolean facts. Facts are listed, and if they're listed, they're true, and if they don't exist, they're false. Okay, so we're not allowed to write that this is a necessary requirement, and in fact, currently, if this wasn't in our state, if holding was not in the state, then we wouldn't be able to check any of the blocks. It is a bit awkward too because holding X had only one block, so you'd have to check not holding all other blocks, which is why we defined the idea that there is the hand empty predicate. Right, so in order to pick something up, it needs to be on the table. It needs to be clear so there's nothing on top of it. And the hand itself needs to be currently empty so that it's available to pick up another block. Cool. All of this is to get to the idea of effects, okay? But effects in strips are a little bit more complicated because we describe them in terms of an add and a delete. This is again based on the idea of this Boolean, well, strictly Boolean reasoning and state description. So what that means is that our effects in PDL will write as effect, and then you can write both positive or negative effects. Here we write them explicitly as facts that we're going to add to the state and facts that we are going to delete from the state, things that we will remove from being true. So initially, right, when you pick something up, well, what is a true statement we want to add? Well, now we know, of course, that if we were to have picked up the block, afterwards, after the action, we will be holding the block. The hand will be holding the block. Okay, so you could have a quick reason about it, but then ends up nothing else we actually need to add as a new fact, right? The only new fact is that the block is now being held. But there are information that we have to delete, right? Or else we now start having these parallel worldviews that make no sense at all. So, on table. Obviously, if we didn't delete this fact, C would still be on the table and it would be held in the sky, which makes absolutely no sense. This is an information we have to make sure to delete, right? So a lot of the issue of strips really is spending the time to properly define these things so that your sequence of state information and the connection points between all the actions actually make sense and overlap with the preconditions and the effects of previous actions. It's rather a tedious business, but it's still a very, very powerful and easy way to represent real-world problems. So what else do we need to delete? Well, it's no longer on the table. Of course, now that we're holding it, right, the crane hand itself is no longer empty. Okay, so that's one. And then the last thing is, of course, that the block is no longer clear. This is an awkward one, but we do want to delete this because if it was clear, you could have other actions that try to put blocks on top of C, right, while it's being held, which makes no sense. So these are all the bits of information that are now true, right? Essentially, these come together. These are just effects. Okay, so this is kind of where strips is coming into play. I want to then start dealing with drawing up a bit of this problem and using these kind of actions to translate things in the state. So I'm going to erase this quickly so that we have the space to work with. First, we're going to define, right, for an environment, every time you want to begin doing the problem, you need to deal with your FOIG, okay? So first, I think I suggest every time you start with reasoning over the world as a human being, try to define all your predicates and operators, right? What are the things you need to reason about? What are the actual constants, objects in the world? And what actions do you think make sense to define? Then you go about doing the initial state and the goal state, which we haven't quite got to. So let's do an initial state over here. And then we'll also do a goal state in a second when I figure out how our room is looking like. Okay, so in our initial state, this is our world at the beginning, okay? If I were to have drawn up what the goal looks like in the end, maybe I'll do it in a small box. But again, the world view, so the crane's empty, and we had stacked everything in alphabetical order, okay? So let's describe this then as the initial state. You're going to see here that this is also a bit of a tedious thing, because you have to list every fact that's true about this world. Okay, so let's start with some easy ones. Let's talk about clear, right? So what I do is I usually look at all my predicates, and then for each one of them, you'll go through and you'll just match things up. If you miss things, it's really dangerous. So don't let me forget. Holding, or hand empty is the one that's always very easy to forget. So clear, this is now where we don't define it in terms of a variable. We have a real problem. We have to actually give the objects the object information itself. So B is clear. In this world as well, C is clear. We also have that E is clear. None of the other blocks are clear. We have on-table information, right? So you'll have to list everything here. So A is on the table, C is on the table, and D is on the table. Okay, so we've done clear, we've done on table. Let's do some on information. Okay, so B is on A, and E is on D. Of course, we look for some other things. Holding, is the crane holding anything? No, at the beginning it's obviously not. And then, this is kind of where I pause sometimes in class to ask students. They would define this, and if you had written up all your functions as well, you'd go to click solve. And instead of giving you any error message at all, the PDDL or strips is just going to return no solution. No solution. Why is that? Because it goes to apply actions. It goes to apply a pickup, right? To try which block can I pick up. It'll try all of them that's available. But it will look for the precondition. Is the hand empty? Because we didn't define this as being true in the initial state, you would never be able to pick up a single block. This is why sometimes it's very hard to debug strips in PDDL. So you really need to make sure, I think when you debug it, you can try to do like almost the print statement equivalent is just changing your initial state and your goal state to be closer together to try to match like incremental steps. But otherwise, I really recommend actually doing what I'm doing here. And then you draw up your state information and draw your connections, as we were about to do, to what actions are actually available to you. Now, let's try to draw up the goal state as well. Is that on the board? Yep. But I will have to be careful. The goal state is just going to be a series of ons, right? So A is on B, B is on C, C is on D, D is on E. Now, E must be on the table, right? It's the bottom one. And technically hand empty. Now this one is slightly different because in the goal, if you didn't care whether or not it was holding another block, say our goal was only to stack A, B, C, D, and E could be anywhere, then you could just omit this and it would actually work. It's a bit different because it needs to be true here so that it works for preconditions. At the end, you can have simple goals if that's something that is really actually what you're looking for. Did I miss anything here? Let me have a look at that. No, I think not. Cool. So also a pretty simple goal. Now, what we haven't talked about is actually how to go about solving this problem. We've finally defined this. This is the problem definition. Okay. We'll talk in the next video about how you apply things like heuristic search, like a simple age-old A-star algorithm to actually solving these problems effectively. And then we're going to look at a bunch of classical planning heuristics, because unlike things in a grid, it's not easy to define heuristics. So there's a bunch of cool ways to do automatic and generalizable heuristic creation. So things like relaxation and whatnot, planning graphs. So that's an exciting future topic. Here, let's talk about how we will be transitioning though. So your computer, again, is completely dumb. These words may have English meaning. To the computer, there is nothing. It is going to look at all of your operators. It's going to look up pick up, put down, stack, and unstack, if we defined all of them. And it is going to attempt to do that on every single object. Okay? So here, it will try to pick up A, pick up B, pick up C, pick up D, and pick up E. Okay, this is why it's dumb. And it will do this for all of the operators. So see how the branching factor of these problems are already starting to explode? And this is why it's hard, because there's so many true facts about the environment. There's so many actions you can do, such a large branching factor. This will continue over time because the computer isn't able to understand the way that the real world works, what we actually might have as promising ideas before we get to things like heuristics. So let's talk about this. So when you go to pick things up, this is the one we wrote down. So we have a bunch of preconditions, right? The thing needs to be clear. So picking up A doesn't meet the condition, it doesn't work. Same with D, okay? So these are pruned, or essentially, right, we don't generate states, we don't take the action. We check the preconditions, we see they don't work, they're not branches we'll look at. Then you have hand empty, which is true for everything. but you also have to check that they're on the table, right? So both B and E, even though they're clear, you actually can't pick them up. So this leaves us with, at least for pickup, there is only one thing that you can do. Remember, you will have a series of other lines as we try the other actions, but we will have a state here. So how do we transition states? It's really tedious again. So we would have this whole initial state, okay? But the good thing is at least now we have our add and delete list to make sense of this. But we look at the initial situation, and we go to add new facts, which I'll do at the end. Let's talk about deletions. So on table, we delete on table C. This, we're going to delete, okay? We're also going to delete hand empty. That's this guy. And we're going to delete clear C. Okay, so how do states work? They, again, are just a giant list of all facts. B is still clear. E, is that E or C? E is still clear. On table, A is still clear. On table, D is still clear. On, B is still on A. E is still on D. Okay. The hand empty is also deleted. But we forgot to add facts. So we also add a new fact. We are holding C now, right? So we have picked up C. This is now the next state that we have arrived at in this worldview. We would continue this over a series of actions. Maybe there's more states down here. This is ... right? Because you'll attempt to look at what other operators you can do from here. And the computer will explore all of these. We're going to essentially try to prioritize which one we expand based on heuristics, which we haven't had a look at yet. But this is strips. The difference, the primary difference in the way strips and PDDL will work is you'll see it happens in the effects. So in the next video, we're going to look at PDDL, the planning domain definition language. We're going to do the blocks world example again, but we're going to show it all looks very, very similar, except we can be much more expressive now in this and through things like typing and a bunch of, it's almost like a Python library. You can start importing useful things that we can define about the world. So thank you for watching. I think strips is quite simple, and see you in the next video.